cannot go too far wrong. Okay, so that is why we care. In the context of estimation, we are now going to get to the context of testing, where we are going to find a similar thing which we would have anticipated anyway from estimation. So what is that? In order to do that, let us again put the three standard kinds of tests that we have seen previously on the table and try to evaluate. Okay, so we have seen Wald tests, you have seen Lagrange multiplier tests, you have also sort of seen likelihood ratio tests. We are going to be more formal about it now. But likelihood ratio tests are really tests like the F statistics that you guys have seen. Okay, so let us see what happens. So the central point here will be that in the domain of testing as well, the likelihood principle is going to provide the best test. In what sense? Well, it is going to provide the most powerful test. So what is most powerful? Let's see, the language of econometrics or the language of statistics is very technical language, right? So we don't take words easily. When we say most powerful, it is not about hitting somebody in the face, right? So power has a very specific meaning. So what was power? You remember your testing lectures? What was the power of a test? Is the behavior of your test under the alternative hypothesis, right? The size was the behavior of the test under the null hypothesis. Power was how it behaves under the alternative. When you are moving from the null towards the alternative, how does your test perform? When you are not in the null hypothesis situation, how powerful your test is determines how effective you are in detecting departures from the null. In that sense, the likelihood principle is also going to provide the most powerful test. All right, so much of what I will say about this will be going in passing here. I'm not going to be very technical about it. But if anybody is interested, I can point you towards appropriate references later on, right? Okay. So let us see. Wald tests, you guys have seen this plenty of times. How do you do a Wald test here? Well, you already have your theta hat ML, right? Under the assumptions of the model. And you have an asymptotic variance of that, which you can estimate. Okay. When you are doing this, you are using an estimate of the true theta naught. Okay, and that is without applying the restrictions tested. Right? So that is under the alternative. Okay. So that is simple to implement. So this is our theta hat ML, which maximizes this quantity here. We know about this. What about the Lagrange multiplier test? The Lagrange multiplier test is going to be exactly the opposite. All right. It maximizes the log likelihood function subject to the constraints being tested using a Lagrangian. Right. So you note down the restrictions. And then you obtain the maximum likelihood estimator by maximizing your objective function, but under the constraints. So that is under the null hypothesis. Okay. So this is a form of constraint optimization. How do you do this? Well, you guys know how to do it, right? So you write down Lagrangians of those, include them into your objective function, and do constraint optimization. So the concept of that is very simple. Yes, please. Yeah.
So our last lab assignment, we saw Lagrange multiplier test for G and M. Would it differ at all between?
The concept is the same. Concept is exactly the same. The Lagrange multiplier what we're doing is you are evaluating under the null hypothesis, so you are doing a constraint optimization there, right? Why it is called a Lagrange multiplier is because you take the first order conditions from the restrictions as well and include that into your estimation. So you are optimizing then not only with respect to theta, your original parameters, but also with respect to how closely you are adhering to the restrictions. All right? And the corresponding Lagrange multipliers, they provide an estimate of the cost. They provide an estimate of the cost of making this assumption. All right? So that is how we understand this. So you can think of these as shadow prices, okay, of the different restrictions that you have placed. All right? So the price is small, then that means that, this is fairly closely adhered to. If the price is large, then you know that these restrictions are not being held up by the data. Okay? So this is evaluating under the alternative. This one is evaluating under the null hypothesis. Okay? If you want to get something more powerful than this, then you have to evaluate, obviously, you have to do more work, right? You have to evaluate under both the null and the alternative hypothesis. Okay? So you have to estimate both your restricted model and unrestricted model. It is like your F-test. Your F-test is a likelihood ratio test. Right. So comments, LM test is performed using this one, which is the true theta naught with the restrictions. So the first order conditions here are just scores, right? So that is why this is also called sometimes a score test, or sometimes even called a Rao's score test, because this part of the theory relating to Lagrange multipliers was developed by Rao. Okay, so right. Let us come to the likelihood principle then. So what does the likelihood principle really tell us? It tells us that if a certain parameter vector gives us a larger likelihood, then that parameter vector must be better or closer to the data, right? That is the likelihood principle, period, right? So now suppose we could evaluate the likelihood under both these estimators. So this one is under the alternative and this one is under the null. Where would the likelihood be larger? Well, of course the likelihood would be larger under the alternative, right? Because it does not have the constraints. How much larger? Well, that is an empirical question, so we can evaluate these two guys. This minus this. This is a strictly positive quantity, right? The likelihood ratio test for A theta equal to 0, this constraint, okay, that is twice the difference of the log likelihoods that converges to a chi-square with r degrees of freedom, where what is r? R is the number of restrictions in this null hypothesis. So why is it called likelihood ratio? That is clear, right? This is the difference of two log likelihoods. That is log of the ratio of the likelihoods. Right? Log this guy minus log this guy is log of this guy divided by that guy, right? So that is the ratio of the likelihoods. Okay? So you are testing whether that is close to 1. Okay? suppose you are using this objective function, your likelihood objective function, instead of the likelihood itself, then you just have to make a small modification, right? So why is that modification? That modification is because when we wrote down this objective function, we divided by n, right? Just to emphasize, because it made life easier, so we could look upon that as a mean, right? Remember this? Yeah, this 1 by n guy, right? You have to put that back in. That's it. Means nothing funny here. Okay. Right. So that is likelihood ratio test. It turns out that this is the most powerful test. All right. Yes, please.
Is there a reason why we multiply the difference by 2?
Because the asymptotic distribution turns out to be chi-square when you do that. Okay? I don't have a better answer than that at the moment, but I'll think through it, whether there is a very clear intuition as to why 2 and not any other number. 2 is quite important because, you see, you want to multiply this with something which typically does not involve the sample size, right? But why 2? I'll think about it a little bit, right? I don't have a clear intuition. Yeah, but it turns out to be chi-square, okay? But this is clear, right? So this one is a positive guy, so this is going to be positive, always. Okay, nice and simple. Let us get to the linear regression case then, right? So this is, well, for me it is very exciting. I'm sure it is for you guys as well. So let us look at this, okay? That's like the Holy Grail, right? Right. Very simple model, right? Okay. No endogeneity, nothing, so just simple yi, and you have a certain number of regressors, including the intercept term, and errors. The full DGP must be specified. So we have, in addition, the assumption that the errors are normally distributed. See, a lot of things are hidden inside this. What is hidden? Well, first of all, homoscedasticity is hidden. No autocorrelation is hidden. This is actually much, much stronger than everything else that you can think about, right? There is no X involved here, so your exogeneity is hidden. It's just a very simple specification, but it hides a lot of assumptions inside. Plus, the shape of the distribution function is also hidden in there. All right. So let us go back to ordinary least squares. So what did we do in ordinary least squares? We computed the OLS objective function, which was the sum of squared residuals at a candidate beta tilde, which is simply observed minus expected squared summed over all the observations, right? In matrix notation, it is simply this guy. Okay, there were a couple of questions here and there today and last time as well about sum of squares, right? The thing that I would like you guys to always remember is whenever you see something like this, that is a sum of squares. Period. That is a sum of squares. If there is something in between, a sandwich, the meat in the sandwich, okay, that is also a sum of squares, but that is weighted. All right? But whenever you see anything like this, that is a sum of squares. That is always a sum of squares. Okay, so it is a distance. All right? Okay. And this we know is minimized at x transpose x inverse, x transpose y. So this is our starting point, and we know that that is not a bad starting point, right? It provides unbiasedness. It provides best linear unbiased estimator, blue, right? It provides asymptotic normality. It provides small sample t distributions. It provides F statistics. And it also provides an unbiased estimator for sigma square. And here I would like you to pay specific attention. You guys know this already, but there is a denominator n minus k here, right? And everybody understands why you have a n minus k, right? So the degrees of freedom adjustments where that comes from, we all know that, right? Okay, so that want to emphasize at this point. Okay, why? Well, one of the reasons is because the maximum likelihood estimator will be different. Okay, so this is our OLS estimator. What is the meaning of this guy? That is best linear unbiased estimator. What does it mean? It means it is the best amongst all linear unbiased estimators. So amongst all linear estimators which are unbiased, it is the best. In what sense? In the sense of efficiency. Right? Together with unbiasedness and together with consistency, I did not add consistency here, but that is kind of a best property, right? So it is somehow quite good, okay? But it is only within a class of estimators, right? So which class of estimators? Linear unbiased estimators, okay? Okay, we understand that. Let us now obtain a maximum likelihood estimator here, because we have a full model. Let us see whether we can do that. So first of all, we rewrite the model in this form. Okay, why can we do that? So our model is like this. Okay, X is given by design. Remember, X is exogenous here, right? X is exogenous by assumption. So Y given X, what is its expected value? Well, its expected value is the same as expected value of, well, Y given X, epsilon has an expected value of 0, so the expected value of Y given X is X beta, right? X beta. And the error itself is IID normal 0 sigma square, IID. So the covariance matrix of this guy is sigma square I. Okay, so it's all independent, identically distributed. Okay, sigma square times the identity matrix. Okay, so what is the conditional density then of Y given X? Remember, how do you do maximum likelihood? You first of all write down the probability, right? Here it's the density, right? So I have to write down the density of the normal distribution. What is the density of the normal distribution? So first of all, there is this product I equal to 1 to n, and then inside the product we are going to write down the probability of each individual observation, right? So each individual observation is what? Yi minus xi prime beta, that is your error, epsilon I, okay? And the rest is just simply the density function of the normal distribution. Okay guys? Very simple? Okay. Now we take terms outside. We take this guy outside. Okay, so that becomes 2 pi sigma square minus n by 2, and then this thing is simply exponential of 1 by 2 sigma square. What is this? Product of these guys. See, there's an exponential here. So the product then transforms into a sum, right? Sum of what? Sum of squares. What is sum of squares? Sum of squares is this guy. Right? So that is just the matrix notation of this particular probability function. Okay? So that is the probability. We want to do maximum likelihood here, right? So what do we want to do? We want to maximize this guy as a function of the parameters. What are the parameters here? Beta and sigma square as well, right? Sigma square is also unknown. Maximize this guy as a function of beta and sigma square given the data. And what is the data? The data are y and x. Okay? So what do? We replace this beta and sigma square, the parameters, with some candidate values. And we take logs, because logs makes our life simpler. Right? We can look at some sums now rather than products. And write this down. So the log likelihood of the data, this is a function of the unknown parameters. This is just simply this guy. So logarithm makes our life simple. Logarithm does not change any other thing. Maximizing the original likelihood function is the same as maximizing the log. So that is fine. Start looking at this. This first term here does not matter, right? Because that does not involve any of the parameters. There is sigma square here in the second term. And there is both sigma square and beta in the third term. Okay? So let us see how we can maximize this. One other thing here, sigma square is a scalar. This beta though is a vector, right? So there are k parameters hidden inside this beta, right? And plus 1. So there's an additional parameter which is in the sigma square. Okay. Maximizing this directly is horrendous. Alright, so we are going to use a technique which is called a profile likelihood or a concentrated likelihood. Okay? So we're going to do this in 2 steps. So in the first step, we are going to assume some sigma square and maximize only with respect to beta. Alright? So if we do this, assume some sigma square, now this term goes away as well, because this is now known, so we have to only maximize this. However, note the form of this. If you want to maximize this, for some assumed value of sigma square, typically we expect that maximized value or the where this beta, so the profile or concentrated maximum likelihood of beta to also involve the sigma square, right? Because we have assumed the value, right? So it should be a function of sigma square. But in this case, life is very nice, because maximizing this guy for a known sigma square does not involve sigma square at all. It falls off. Do you guys see this straight away? Why? Because, first of all, we have already assumed the value of sigma square, so the second term does not matter, right? We are trying to maximize this as a function of beta, right? In the third term, this is only a scaling factor. So maximizing that is the same as maximizing this guy. What is maximizing this guy? Well, maximizing means there's of course a minus here, right? So this is minimizing this guy, right? What is minimizing this guy? So that is OLS. Together, guys? So the maximum likelihood estimator of beta for any value of sigma squared does not involve sigma squared at all. It is this guy here, right? This would not happen normally. In other applications, you would find that when you try to maximize this using profile likelihood or concentrated likelihood, you would find a solution which also involved the sigma square. Right? But in the normal linear regression case, life is nice, so this just falls off. Okay? So, you ask the question, does this maximized value depend on sigma square? Well, let us find out. So maximizing this is the same as, minimizing this guy. We are lucky, we already know the solution. This does not depend on sigma square at all. Okay, so we have been very lucky here. So, we now know what value of beta maximizes this guy, right, for any sigma square. But that is only one part. Now we have to find out what value of sigma square now maximizes this, but that is simple, right? Because now it is only a scalar maximization. The hard job is already done. Okay? So let us do it. So, we can now plug this into the objective function, maximize with respect to sigma square. So the concentrated likelihood now, in terms of sigma square only, has this second term here. That is important. And the third term is also important. But what is here? This guy does not depend on sigma square. This is like a constant, right? So this we already know. Okay? So maximize this. That's a simple maximization problem. It turns out that it is E prime E divided by N. Hang on a minute. What was this? Sum of squared residuals divided by N minus K. What is this? Sum of squared residuals divided by N. So what happened to the K? Well, it's just a different estimator. Okay? So, the least squares estimator of beta is the same as the maximum likelihood estimator. The least squares estimator of sigma square, however, is different. Right? It has a different scaling factor. Right? In OLS, this was divided by N minus K. We lost K degrees of freedom because we were estimating K parameters in the beta, right? We lost K degrees of freedom. Here in maximum likelihood, we don't lose that. So this is just N minus K divided by N S square. Okay? Or OLS estimator. So what are the implications? Well, first of all, with regard to this guy, this is obviously biased. How do we know this is biased? Because the OLS estimator was unbiased. Okay? So if you have a scaling factor there, it is going to introduce bias, right? So this is biased. So then the question is this therefore not desirable? Which would you prefer? Okay, there are several ways to go about this. One is to think what happens when n goes to infinity. What happens to this when n goes to infinity? This to become the same, right? So there is a small sample bias in the maximum likelihood estimator, right? But that goes away when n goes to infinity. What about the beta estimate? So OLS estimator, we already knew that that was best linear unbiased estimator. Okay? Now we know that this is the best unbiased estimator, at least asymptotically, because it is the most efficient. It still needs to be unbiased, right? Why do you need to be unbiased? Well, or something like that, at least consistent. Why? If you do not have something which pins down the center of your estimator, you get complete garbage, right? Think of this estimator. My estimator of beta is 1. What is the variance of that estimator? 0, right? But that is a complete garbage estimator, right? Why? Because it does not converge to the true value, right? It is not unbiased, it is not consistent, it is just plain garbage, right? So you need something to pin it down, right? And this unbiasedness does that function, performs that function. Okay? So what do we gain out of doing this? We get a best unbiased estimator. However, we also have another estimator here, right? That is the GMM estimator. What about the GMM estimator? We saw that that is also the OLS estimator, right? They are the same. Because the OLS and the GMM are the same, so, and the GMM is asymptotically efficient, so we are not really gaining that much, right? Okay? So whether there are finite sample gains or not, we will look at that a bit more in detail now. Okay? But so far so good. Alright? Nice and simple. Okay? Right. Okay, how good is the OLS ML estimator? In order to understand that, we have to look at a couple of concepts. One is the Kramer-Rao inequality. All right. This guy Rao is a very important guy in this literature, right? So it is the same as the Lagrange multiplier Rao. So Kramer-Rao inequality and also the information matrix equality. Okay. So let us see what it says. Okay. Here I start becoming slightly more technical in the statements, but I am not going to provide proofs of most of the things, right? But at least conceptually we need to understand this. Why we want to be a bit more technical is because these principles actually apply very broadly, right? It is not only to, kind of the simple models that we are looking at now, it applies to a lot of models, right? So all models that you guys are going to study anyway. So let Z be a vector of random variables. They are not necessarily independent. Okay, think time series here. Okay. And the joint distribution is given by this guy. Standard, right? So that is the joint distribution. Okay. What is theta? Theta is a parameter vector. That is an m-dimensional vector of parameters in some parameter space. Okay, so we are being very general. L theta tilde, this is the likelihood now. That is the counterpart of the probability function here, right? Is the likelihood function. And this guy is an unbiased estimator of theta with a finite variance covariance matrix, any unbiased estimator. Then, under some regularity conditions on the density, on the model, I'm going to be more specific about this a bit later, and under the condition that the true parameter value does not lie on the boundary of the parameter space. It looks a bit technical, right? But it is quite important. The true parameter value should not lie on the boundary. So for example, in a linear regression case, you should not have a situation where sigma square equal to 0. What is that situation, sigma square equal to 0? There is no error. All right? So there must be some random error, right? Okay, for example. So the true parameter value does not lie on the boundary of the parameter space, then variance of this estimator here, unbiased estimator, cannot be smaller than this guy. What is this guy? Well, this guy is that the true parameter value, first of all, it is the expected value of S theta naught prime. What is this? Okay, I'm going to come back to this. All right, this quantity. But S is itself is a score, right? So, all right. And together with that, we have an information matrix equality, which says that under the same regularity conditions, which regularity conditions? There's some conditions which I did not state here. Where was that? Yeah, some regularity conditions. This and this. The information matrix equals the negative of the expected value of the Hessian. This is a guy that you have seen earlier, right? Where have we seen this? Where have you seen this guy? In the asymptotic variance of the maximum likelihood. This is exactly, this inverse of this is exactly the asymptotic variance of the maximum likelihood. So what's going on here? The variance of an unbiased estimator cannot be smaller than the variance of the maximum likelihood. What does that tell us about the maximum likelihood? It is the most efficient estimator, exactly. In a class of asymptotically unbiased estimators, it is the most efficient estimator. It is not only the best linear unbiased estimator, it is the best unbiased estimator. Provided, of course, that these conditions hold. Okay? So then this is therefore called the Kramer-Rao lower bound. This is really a benchmark for any unbiased estimator, right? Any unbiased estimator cannot have a variance smaller than the Kramer-Rao lower bound. Okay? Right. What are the principal regularity conditions? The support of the random vector Z does not depend on theta. What is that telling us? That is telling us that if Z is somehow restricted, okay, how much Z is restricted does not depend on theta. you should not have a situation that if theta takes one value, the random variable takes a large number of values. If you have another value, it takes a small number of values. If you have one value, it has support on one side of the sample space. If you have another value, it takes support on another part of the sample space. Okay? Are these reasonable? Well, in the kinds of models that you guys are going to look at, yes, they are reasonable. In, for example, Markov switching models, they are not reasonable, right? So there are other kinds of models that people use where they may not be reasonable. But that is one assumption. Secondly, the density function should be smooth. How smooth? It should be at least 3 times differentiable with respect to theta. Or otherwise, at least twice continuously differentiable. Okay, so it should be smooth. And the true theta naught must lie on a compact set, that is, theta naught does not lie on the boundary of the parameter space. Okay? Right? So those are the principal regularity conditions. And we are going to brush against that even in simple examples, and we are going to see that in a little bit. Okay? Right? Okay. So why is this relevant? Well, you guys know the answer now. So we'll now be a bit more technical in describing the asymptotic properties of the maximum likelihood. X1, X2, Xn is an IID sample with the probability density function, this guy. General setting. The maximum likelihood estimator is consistent, provided 2 conditions are satisfied. One is that this guy here, this is our objective function, right? Maximum likelihood objective function, that converges to expected value of log fx. That should really happen, no? Yeah? This is like a sample mean. Okay? If it has a expected value, then this guy should really converge to that. Okay? But it says that it should converge uniformly in theta, right? So at the same rate for all values of theta. So this holds in most situations. Why? Because sample means converge to population means. Second, this guy should be uniquely maximized at theta equal to theta naught. So in other words, there should not be a space within the parameter space where this guy is maximized, right? There should be a unique point. In other words, this is talking about convexity of the objective function itself, right? Okay. So that is number one, so that is consistency. Asymptotic normality. This guy has the distribution that we expect, right? So this is asymptotically normal, that means 0. So it is asymptotically unbiased, right? And this guy is the asymptotic covariance matrix is just the inverse of the negative Hessian, all right? Evaluated at the true value. Okay? Another way of stating this is that theta at ML is asymptotically normal with a mean of theta naught and a variance covariance matrix, which is this guy. And that is the information matrix of the sample. So naturally, now we expect that the maximum likelihood estimator may attain the Kramer-Rao lower bound, right? Because the covariance matrix looks very similar, right? Okay? So indeed this is asymptotically efficient in the class of consistent and asymptotically normal estimators, right? It has the smallest asymptotic variance amongst all consistent and asymptotically normal estimators. Now let us see whether we can verify the Cramer-Rao lower bound properties of our linear regression estimator. Okay? So that has to do with, so these are the asymptotic properties, right? Now we'll look at the finite sample properties. Okay, so what happens in finite samples? Okay, so let us look at the Cramer-Rao lower bound in finite samples. So back to where we started from, this was our likelihood function. Okay, so there are two purposes of doing this here. One purpose is to get you guys comfortable with analytical expressions of this kind, right? So like linear exams, you will not get the normal regression problem, but you may get a likelihood problem where the likelihood function is a bit simpler, but you should be able to do these kinds of calculations. Okay, so we are going through this in a slightly more complicated case, all right? Okay. But every step to every step is very simple, as we will see soon. So we want to obtain the score vector. How do you obtain the score vector? Well, you take partial derivatives, right? So I'm going to take partial derivatives by partitioning my parameter vector into two parts. My parameter vector theta is equal to beta and a sigma square, right? What this beta itself is, has k parameters inside. Okay? But as we have seen, these two work in different ways on the likelihood, right? So I'm correspondingly partitioning my score vector like this. So this part here corresponds to the beta, and this part here corresponds to the sigma square. Okay? The rest is just taking partial derivatives. If you want to take partial derivative of this guy with respect to beta tilde, right, that simply, or with respect to beta, that simply turns out to be this guy. Okay? This part drops off. Okay? This is a constant term here, right? That goes outside with an inverse, all right? There is a 2 here which cancels against a 2 which comes from here. Why does a 2 come from here? Because this is a sum of squares. Okay? Now at home, try to do this properly, right? Once you do this, you are going to find exactly this expression here. That is the partial derivative. What about sigma square now? Now this term does not contribute anything. This term contributes something, that is this. And this term contributes something, but now we are holding this as fixed because it's only a partial derivative, right? And the rest simplifies. So this is the score vector. What else do we do here? Well, now we simplify, right? How are we simplifying? We are writing y minus x beta as an epsilon. Because remember that where is the randomness here? It is in the epsilon, right? X is fixed by design. The randomness here is only in the epsilon. So, in the errors. So we are writing this in terms of the errors. So this becomes epsilon prime epsilon, and this guy becomes x prime epsilon. Okay? Okay. Now at the true value, at the true parameter value, what do we expect the score to be? See, why did we obtain this score? We obtained this score because we want to maximize the likelihood function, right? And we equate this score there to what? To 0 to obtain the likelihood estimator, right? So the true parameter value, this score should be 0. In expectation, of course, because this is a random quantity. Right. What happens here? This guy is going to be 0. What about this guy? So think of this intuitively. What is this? This is sigma square, right? Right? So one sigma square is going to cancel against that. And then there will be an n here as well, because there are a lot of sigma squares that you are adding up, right? Okay? So these two are going to cancel off as well. So in expected value, this will be 0 at the true theta. Okay? Right. Under the assumptions of the regression model, expected epsilon equal to 0. Expected epsilon prime epsilon is n sigma square, right? I've provided an explanation for this, but you can come at it in any way, right? Okay. And this guy is 0, right? That is exogeneity assumption. Okay? Under those assumptions, expected value of the score is 0. That is exactly what we expect. Yep.
Is that now strong exogeneity?
Yes, yes, yes. Excellent. Yep, that's life. Right? 5-minute break. All right? Okay, so far so good? Okay? Right. Right, guys, let us get on with it before you start forgetting where we are. Okay? So we are halfway through on the linear regression case, right? So we have looked at this core vector. We are happy that that is in expectation 0. Good. What about the Kramer-Rao lower bound? For that, we have to go to the Hessian. All right? Once again, I'm going to partition the Hessian matrix. Remember, that is K plus 1. So this guy is K plus 1. K plus 1 times 1. So the Hessian matrix will be K plus 1, K plus 1. I'm going to partition this again into 4 blocks, right? So this will be the scalar, right? And this will be the cross terms, and this will be the K plus, well, this will be the K by K term, right? The rest is nice and easy, okay? So you're just going to take these guys and take first order derivatives, all right? Or take this one and take first order derivatives, yeah? Okay, a bit messy, but that is how it looks. Del beta prime. What was our first term here? That was this guy here, right? We're just writing that here, okay? Partial derivative of that, that is simply sigma inverse x transpose x, okay? The cross product terms, or the cross derivative terms, we expect them to be the same. One to be the transpose of the other, right? Because if whether we take the partial derivative of one and then the other should not really matter. In regular cases, it does not matter. So that is taking the same term here, and now taking partial derivative with respect to sigma square, that gives us this. If you take the other term and take partial derivative with respect to beta, you get this, right? So these two are very similar. What about the final term? So that is this, okay? And just taking partial derivative of that with respect to sigma square, that is easy. So this is scalar, right? That gives us this. So we have all the parts of the Hessian matrix. So now we take expectations minus expectation of this guy. Okay? What is this guy? This guy is whatever it is. That is our design matrix, right? Okay. What about this guy? Expectation of these two guys are 0. Exogeneity. Okay? What about this nasty object? Well, expectation of this is n sigma square, right? So terms cancel and this becomes this. Okay? Couple of things to note. Yes, please.
So x prime epsilon and epsilon prime x have different dimensions, right?
Yes.
So we just don't really care what's in there because their expectations go to 0. We don't really mind too much what's in them because the assumptions give us that their expectation is 0.
This is 0. This is a k by 1 vector. This is a 1 by k vector.
Okay, so they still have different
Dimensions, yes. They have different dimensions, of course. This is k by k, and this guy is just 1 by 1. All right? So I'm partitioning the matrix, right? Just to be able to look at each of those separately, right? These two are 0, that has very important implications. See, concentrated likelihood really worked here. Why did it work? It worked because these two guys are 0. If these two guys were not 0, it would not work. In general, it would not work. Okay? So really, the fact that these two guys are 0 is an artifact of the setting of the problem. We have made assumptions so that these are 0. So that is the strong exogeneity assumption that we have made. Okay. So this is block diagonal in beta and sigma square, which is important because that is what gave us the specific advantage in this case. We could do profile likelihood or concentrated likelihood. So what are the Cramer-Rao lower bounds for these guys? For the unbiased estimator, this is the Cramer-Rao lower bound for the unbiased estimator. Question is now whether the maximum likelihood estimator satisfies these lower bounds. That needs to be verified. Okay, so we'll try and verify that. So do the MLEs attain these Cramer-Rao lower bounds? Well, first of all, this guy is unbiased and variance of this guy is, okay, OLS lectures, right. So that is precisely this. Okay, so you cannot do better than this. Okay. So this then, the maximum likelihood is the most efficient unbiased estimator. And that is an advantage, that is the advantage that we get in maximum likelihood is that there was a linear here that we have got rid of, right? It is any unbiased estimator, okay? Remember that there are other unbiased estimators here. Means of course, you know, the GMM is the same as this, right? But there are quantile regression estimators as well, which are unbiased in this context, right? For example, the median or mean absolute deviation estimator is also unbiased here. So compared to that, ML or OLS is more efficient. Okay. Right. What else? Remember, this guy is not unbiased. Remember that, right? Okay. So it cannot really compare. But still, it is worth asking what would happen if we had an unbiased estimator. So we have an unbiased estimator here, which is S square, right? Okay? I'm not going to show this, but just stating this here, that the variance of S square, you guys might have seen this earlier, is this guy here. So that is larger than this, which is this. Okay? So S square, which is an unbiased estimator, does not attain the Cramer-Rao lower bound. The question which arises is, can you do better than this? Well, it turns out no. This is the best estimator in this particular context. You cannot go better than this. So just because there is a Cramer-Rao lower bound does not mean that it can be attained. Intuitively, why does this happen? Well, this happens because sigma square can take values arbitrarily close to 0, and that is very close to the boundary of the parameter space. So if it were separated and somehow were in the center of the parameter space, this would not have happened. Okay, so that is why we cannot attain this lower bound. So this guy is, of course, what is the variance of this? The ML. So that is this guy here, right? That is smaller than 2 by n sigma power 4. So the variance of the maximum likelihood estimator is smaller than the Kramer-Rao lower bound. Is this somehow something which is important? No, because our maximum likelihood estimator is not an unbiased estimator. Okay? Well, if we were not caring about unbiased estimator, we could make that 0, right? Just set sigma square equal to 5, that would have a variance of 0, who cares, right? So that is not a good estimator. So, this is all right. Second, I'm not going to show this, but an unbiased estimator with a variance lower than this does not exist. So the OLS estimator of sigma square is the most efficient in finite samples. So the Kramer-Rao lower bound is not always achieved in finite samples, and S square is the most efficient estimator. And third, ML achieves asymptotic efficiency, okay, under the assumptions that the DGP is appropriately specified, plus all the other regularity conditions that we have maintained. So then what do we prefer and why? Well, that is a question for you guys. Okay? But one can go into a nuanced answer here. Finally, the GMM that coincides with the ML estimator if the moment conditions happen to coincide with the score vector, right? So what is the score here? This is the score. Okay? This is equivalent to what? This is equivalent to expected value of this guy is equal to 0 and expected value of this guy is equal to n sigma square. What is the standard GMM estimator that you guys have looked at? That used only the first set of moment conditions here, right? It did not use the second, right? But now that you know how to do nonlinear GMM, you can do a GMM here, right? So the moment condition here are nonlinear. That is why we did not do that earlier. Okay? Remember, this is in terms of epsilon squares, right? So these are complicated moments, right? Okay? So, but you can do that. So you can do a GMM here, and that will be exactly the same as the maximum likelihood. Okay? So therefore, the GMM provides the same estimator in this case under weaker assumptions, and this estimator is asymptotically efficient. So whichever way you look at it, OLS is about the best that you can do here. So what does maximum likelihood provide? It provides a benchmark, right? So we know why it is best, why OLS is so good. Okay, in some ways. The reason this happens is in this particular case, the GMM and the OLS and the ML all coincide, right? Okay. So basically the OLS gets the good properties of all the three, essentially. Okay. A very quick, just a statement of quasi-maximum likelihood. It's really an extension. So the ML results assume normality of the error term. Without normality, of course, there is no guarantee that the ML is the same as OLS or the estimator achieves the Kramer-Rao lower bound. But still it is a good estimator, right? Because it is GMM. We know that the OLS estimator is good. So even if these ML conditions are not satisfied, it can still be a good estimator. And that is the principle behind quasi-maximum likelihood or pseudo-maximum likelihood. So an estimator that maximizes a misspecified likelihood function. In this case, the misspecified likelihood function would be, the likelihood function is misspecified because it is some other distribution, but we have assumed normal, right? But it works quite well. So the ML can be good in this, can be consistent under the true model in this case, for example, if it coincides with the GMM or independent data settings, we can have the same situation. So the theory then is provides a benchmark, right? So it can be interpreted as providing finite sample properties of the quasi-maximum likelihood estimator when the error is incorrectly specified as being normal, right? So it's like the counterpart of, well, Newtonian mechanics in modern physics, for example. It provides a benchmark, okay, so against which you can evaluate. So everyone together on this example? Shall we go back to the binary case? A bit more flesh to that now. All right, do some regression, binary regression. Okay, let us do some maximum likelihood there, okay? Right. So previously, we just had this, right? Now we are going to include some regressors. Simple extension, and let us see how it works. The questions we are asking is, does a job training program make someone more likely to obtain a job? Price, distance to work, and provision of public transport, how does that affect your choice of whether or not to buy a car? Things like that, right? How do children and other domestic arrangements affect the decision to enter the labor market? Okay? The moment you see these kinds of problems, you think, oh, hang on, let's do regression. Okay, so let us see what regression provides, right? So let us do OLS. I've said that in fact it is not a bad choice. Okay, so let us see how we can formalize this. So let us say that our dependent variable is working. Okay, so it is 1 or 0, right? So it's binary. But beneath this binary dependent variable, there is something else lurking, right? So there is an economic model behind this. So let us try and think through this economic model a little bit. So one way to do that is to think of a latent variable yi star, which provides an utility from working. All right? And an individual works if this utility is positive and does not work if the utility is 0 or negative. Okay? And let us also say that there are 3 regressors that we collect into our X. So yi is equal to 1 if this linear function is greater than 0, and yi equal to 0 if this linear function is less than or equal to 0. This is like a standard regression function, except that I have done a little bit of trick here by setting the error as a negative. Does it matter? It does not matter. It matters for, we are going to see in a few seconds why I do it in this way, but it is a zero mean error really, right? So whether you set it as a positive or a negative does not matter, right? It makes notations easier. Okay? Okay. So yi equal to 1, the probability of that is the probability that yi star is greater than 0, given your x's, which is really the probability that xi prime beta is larger than epsilon I. All right, so you have a random shock coming to you as well, and your utility from working is larger than this random shock. That is a function f. So let us write this as a function f of xi prime beta. Okay? And then the other part of it is really just 1 minus f of xi prime beta. So that is the probability yi equal to 0 given your xi's. First of all, what is this f? This f guy is really a distribution function, right? It is any distribution function. First of all, it's a probability. All right? And the larger its argument, okay, the smaller it becomes, so it is really like the inverse of a distribution function. All right? It goes from, decreases from, it increases from 0 to 1, right? Now what we can do is that we can substitute different functional forms here. And we are going to take several functional forms. And by taking several functional forms here, we are going to get different models. The linear priority model, the probit model, and the logit model. So let us see what these are. The probit model assumes that the error term has a standard normal distribution, this error term. Sorry, okay. This error term here. Now this really looks like the linear regression model, right? It even looks like the normal regression model that we just looked at earlier. But there is one critical difference. What is that? In the normal regression model, the variance of this epsilon guy was identified. So it was normal 0 sigma square. It is not identified here. Why? Because you can just, increase the scale of these by taking larger betas, right? The scale is not identified in this case because your dependent variable is only limited, right? You just observe 1 or 0. You do not observe how far away from, so you do not observe the scale. All right? Because you do not observe the scale, you need to set the variance at some arbitrary value, and we are setting that scale at 1. Okay? So then my fz is simply the normal, standard normal, cumulative distribution function. Okay? Phi of z is minus infinity to z, the standard normal PDF du, which is just simply this. Now that's not the only thing that we can do. We can assume something else as well. Another very popular choice is this guy here. So that is the logistic distribution. There are some advantages to this. Well, there are two advantages. One is that this form is very nice, so taking derivatives, etc. is very easy. There is another advantage as well, but which I have never understood very well because I don't do betting. But apparently people who do betting understand log odds very well. All right? I don't understand log odds, but there is an interpretation of these in terms of log odds or odds of winning a bet. Okay? So I don't work in the betting market, I don't understand it very well. But people who do find this very natural setting to look at. Okay? Okay. But let us go back to something that we can do very easily here, which is just think of this as a linear regression problem. So this is our linear regression problem. And my yi is 0 or 1, right? I have an error term here, and that error term is, let us say, normally distributed, or any other distribution with mean 0. All right? So what I can do is just plug in 1 and 0 and just regress. Is there anything wrong with doing that? Well, no, this is a perfectly defensible procedure. There's a nice discussion that you can find in MHE, and there are some positives. One of the positives is, of course, with respect to robustness, and the other one is ease of interpretation, but which cuts in two ways, as we are going to see very soon. if we did that, then of course, what would the beta k tell us? It would tell us directly the impact of a change in xi on xik on yi equal to 1 occurring. So that is a nice marginal effect. So let us say yi equal to 1 is finding a job. Xik is a person going through a job training scheme. If you had your beta k equal to 0.15, it says that, well, if you went to a job training scheme, your probability of finding a job would be 15% higher. Okay. But that straight away, that simplicity hides the problem, which is here, one of the significant problems, which is that suppose your probability after doing your MSc economics here of finding a job anyway was 0.9. An additional job training scheme can certainly not increase the probability to 1.05, right? So a marginal, constant marginal effect may not really be what you are looking for here, right? It may not correspond to reality, okay? Similarly on the lower side as well, you can imagine situations happening like this. So this, the other problem is that this thing, so another way of stating this is that this is fine to think of this as an average treatment effect, right? But you cannot really think of that as the marginal effect for each individual person, right? There are a couple of other things, and at least three important things. One is that there is a problem of heteroscedasticity here. Why? So the conditional variance of the error, what is the conditional variance of the error? That is p times 1 minus p, right guys? You remember your Bernoulli, right? P times 1 minus p, okay? What is that? That is this guy. Now this guy is going to depend on xi, right? So you have heteroscedasticity here. Okay. Fine. We can still use the linear probability model. However, we should account for heteroscedasticity by using some kind of robust standard errors. Okay. Second problem is, as I was mentioning, the effect will not be the same for everybody. Right? The predicted probabilities will go above 1, some cases below 0, right? So the marginal effect should not really be the same for everyone. And that fact of real life is not captured in this model. Okay? Same example here. In other words, the marginal effect is simply the OLS coefficient this, it is the same for everybody, and it is not quite reasonable in this context. Okay? There's a third problem here, which is related to the first one. See, we know that our yi is 0 and 1, but somehow we are pretending that our dependent variable is a continuous random variable and doing least squares. So we are not using the full information that the data provides us. Right? Because we are not using the full information, what is going to happen? The linear probability model, the estimates will be less efficient. You are not using the full value of the data. That's number one. Number two, anyway there is heteroscedasticity, so you are going to use robust standard errors. And robust standard errors will be much larger than your OLS standard errors. So you get a double whammy here, right? Okay? So even if this is somewhat efficient, you cannot use the standard errors. So you are going to make much more conservative inferences, and therefore you are really not using the full value of your data. All right? Since we are using the distribution, so there is an F we have seen earlier, so the maximum likelihood is a natural approach to take. So let us see how we can go about this. This is a very simple illustration of the problem, right? This is your linear priority model, right? Okay, so that is a linear link function, right? It goes below 0 at the lower end. It goes above 1 at the upper end. That is why you have predictions which are outside the range. There is heteroscedasticity, you can fix that. Out of range predictions, you need logit or probit. Inadequate marginal effects. How do you solve this? Well, you need to really use something which tapers off, right? Okay? Fine. We use something like this, but that is very easy to say on a graph, right? Which function do you use? There are thousands of functions which go like this, right? So you need to assume something. So you assume, let us say, the normal, and you get the probit model. You assume the logistic, you get the logit model. They look sort of similar. We do maximum likelihood. Wonderful. Efficiency, we gain efficiency, asymptotic efficiency certainly. But what if our assumptions were wrong? Okay, so there is no free meal here. You can gain efficiency, but one has to put that in the context of this specific application you are looking at. So, let us see first how we do this. Instead of the LPM approach, we use this as an argument to a function f that tells us the probability yi equal to 1. Okay, this function is going to increase from 0 to 1 as the argument goes from minus infinity to plus infinity, right? Like this, right? So it tapers off, and here. Okay? And once we have this, if we have estimates of this, then we can find out the probability, predicted priority, so on and so forth, and predicted priorities are exactly between 0 and 1. So that is nice. Okay? So any cumulative distribution function will do. Let us take a couple. First of all, let us write down the likelihood function. Very simple. Li beta when yi equal to 1 is f, right? Li beta when y is equal to 0 is 1 minus f. Okay, now we take the functional form. Before we do that, this is Li beta then, f to the power yi, 1 minus f to the power 1 minus yi. Why? Well, yi only takes values 0 and 1, right? When yi equal to 1, you get this. When yi equal to 0, you get this. Same as this. All right, so that is a simple way of writing this compactly. Okay? And then the rest is simple. We assume IID. So this is our likelihood of the data, likelihood of the parameters given the data, right? And then we take the log likelihood, then we construct Qn and maximize. That's it. Problem is that there is no closed form solution. Okay, so Stata goes on cranking and gets you an answer, right? So numerical maximization. what link function should we choose? Well, we can choose the probit. If we choose a standard normal CDF, right, that is the probit. If we choose the logistic, that gives us the logit. If we choose an uniform CDF, provided we can do this really, really well, we will get linear probability model. Really, really well meaning that we have minimum chance of minus, probabilities turning negative or above 1, right? The slope, you control the slope. Okay? Right. LPM still has some disadvantages, I've said, so it is rarely used. You use probit or logit. In practice, it normally does not make much of a difference. But I'll come back to this issue later on. This probit has an advantage, is more traditional in economics. Logit is the default in other disciplines, for example, in biomedicine or in ruin probabilities, some of the stuff like that. People use it quite a lot. There's an interesting question here. Is the link function identified? It turns out that the link function is actually identified from the data. I'll come back to this issue later on. But it is enormously difficult to implement. All right, so there are many problems in econometrics where things are identified but very difficult to implement. So this is one of those examples. Okay. So how do we go about this? Essentially a latent variable model. Your yi star is the true utility. You don't observe that. You only observe whether that is larger than 0 or smaller than 0, right? So whenever this threshold flips, the yi flips from 0 to 1. Okay? This is not an alternative to the probit model. This is the same as the probit model. It's just an alternate statement of the probit model. So this is the probit model, essentially. But this allows us to think through these kinds of quantities in a nicer way, right? So. Okay. One other point I should have mentioned in the graph here. So the big advantage here is that you note that the marginal effects are different at different places, right? Right? The marginal effects are small here. They are also small here. But they are large here. So the center, the marginal effects are the largest. Okay, so that is what this is capturing. Okay. Right. What else? The rest is simple. Beta hat k is not the marginal effect of x. Marginal effect is different for different individuals. What is the marginal effect? So that is del f del x. That is beta hat k times this guy. And this guy is a CDF, so this guy is a PDF. So f is a CDF, so this is a PDF. It is different for different individuals. Okay, so and in the labs you are going to see how to compute marginal effects. So this is your marginal effect. Okay, but in a linear probability model, the marginal effect will be same for everyone. So marginal effect depends on x. So you have to choose which particular x or which particular individual you want to compute the marginal effect for. And that is one of the reasons why you justify maximum likelihood here, because you want the marginal effects to be different, okay, because that is more realistic. Why do you evaluate? You may evaluate at a sample mean to get an average marginal effect. You may evaluate at actual sample values to get the marginal effect for each individual, each student separately, for example, and then average across all of these students to get an average marginal effect, or evaluate at some set of characteristics of interest, right? It's a particular policy situation, let's say. Okay, so now what happens here? So this is our likelihood function, where f for the moment for the probit model is like this, and f is this guy for the logit model. Either case, we can write down the log likelihood. Very simple, really. Okay, so because this is a power here, so yi log this plus 1 minus yi log this. Okay, and then you get some simplification. If you take the first order derivative, for example, this is all minor details. Every step is very simple, and finally you get something like this, and that you set to 0 and solve. However, see that these things are not easy things to work with, so still you have to do numerical maximization in general. For the probit, you have this quantity, that is your objective function. You have to maximize it numerically. For the logit, it simplifies a bit, comes out to be this, but still this has no closed form solution. So again, you have to go to your computer and find out, kind of maximize this. What about consistency and asymptotic normality? Well, you are doing maximum likelihood. So if you satisfy the conditions of maximum likelihood, then you get consistency and asymptotic normality. They can be verified in this case. It takes a little bit of algebra to do that. I'm not doing it in the lectures, but Hayashi has, kind of details of this, so you can check. One of these, I think Hayashi does the logit case in the text, and the probit case is in an exercise, but check that. What about the OLS, or what about the linear probability model? What does that maximize? So that, what about GMM? So you can estimate the probit model by GMM. Why? Because what you are, your moment conditions are these, right? And you can do nonlinear GMM here. Okay, there is an exactly similar formulation for the logit problem as well. So you can do GMM under a very flexible. So GMM is simple. It has less reliance on the differentiability conditions, right? And you can go ahead and do GMM here. What you can also do is, because GMM is easy here, you can have a very flexible link function. For example, you can have a link function which looks like this. So this is 0, this is 1. It's I have piecewise linear things. I divide it into a number of pieces, and I let the number of blocks, pieces go to, the sticks go to infinity as n increases, right? So you can do that at a particular rate, and you can do this with a very flexible link function. And that will provide, in principle, a test for whether the logit assumption or the probit assumption is appropriate as well, right? So you can do a test of that along the lines of Hausman. That's simple. You are going to see this in labs tomorrow, right? So, how you do it in practice. I will probably use, are there questions at this stage? You guys get the general idea of maximum likelihood? The properties of maximum likelihood, what maximum likelihood can deliver, what to cover against, the strong assumptions. So you assume the full model, right? The full DGP is assumed. So that has implications. So be careful about that. Otherwise, things are nice and fine. I'll probably take 5 more minutes just to highlight a couple of additional things. Just a couple of examples, really. One is a random utility discrete choice model. All right. What do you do in this? one way of looking at binary response models is through discrete choice. So for example, you have a wage outcome. So if you look at the decision to work again, you can take this to a utility framework by considering two equations. One providing a utility from working, all right, and that is in terms of a wage outcome. So you think, given your particular context, what kind of wages can you get? And then you balance that against your reservation wage. And if your wage turns out to be larger than your reservation wage, then you work. Okay, so these are things which determine your wage outcome, right? So this is a Beckerian equation. So this is education, experience, so on and so forth. And reservation wage depends also on endowments and so on and so forth, right? So you have a reservation wage, you think means below this particular wage rate, I'm not going to work, all right? What do you observe? You observe the decision to work, which is whether your wage outcome is larger than your reservation wage. Okay? Then the question is, if you are setting this up as a binary response problem, what can we identify and what not? So yi is 1. So what am I doing here? Basically, you are taking the two equations and subtracting one from the other, right? Okay? If this guy is larger than 0, you work. If this guy is less than or equal to 0, you do not work. This is very similar to what we have seen earlier. However, there is one very important thing here. Can you identify these two separately? No. What you can identify from your data is only the contrast. Okay? So if there is, so that is for the intercept. What about for each of these variables? If the same variable, if education affects both your reservation wage and your wage outcome, then you cannot get the estimates separately from this model. Why does that happen? That happens because you have a limited dependent variable setting, right? You are not observing the full data. You have not observed your potential wage. You have also not observed your reservation wage. You have just observed whether the potential wage is larger than the reservation wage. Okay? So the contrasts are identified, and you can identify them using the kind of probit, logit, whatever. But in a random utility model, you cannot as such get down very easily to the underlying structural model in a sense. Not done the identification lecture yet, but this will become clear when we do the identification lecture. Right, but this is sort of the starting point of a large amount of literature which is on discrete choice models. So you can come closer to identifying the structural form when you have multiple choices. And that was the fundamental contribution that, for example, McFadden made. Right? Hickman and McFadden received the Nobel Prize in economics, well, when was it? 90s, early 90s, right? And McFadden particularly for his fundamental work in this area. And that is the starting point of a huge literature which I do not go into, but you guys might want to do that, in your projects or elsewhere. That is one. And finally, there is a sample selection model which is due to Hickman, which I have left as self-study. This is slightly more complex than what we have done so far, but you need to really have some practice with working with these models, right? So I am not going to do this here, but things like this. Where is it? Things like these. You should actually be able to have some practice with computing, right? So this is left with you guys to go and do some practice, all right? One step to another step is very easy, and in exams, this particular example will not come, but there will be other maximum likelihood questions where you will need to do calculations of this sort. You have seen some of these in the linear regression case. Well, you have seen some of these here, right? You have seen some in the linear regression case. Yeah, this guy is here, right? Okay, so I need some practice. Okay, so each of these cases are simple once I've written the model down, but it takes some effort to do it. So I'll leave it at that and then proceed further. Questions, comments? Yes, please.
So next week, are you going to panel data or back to the GMM specification?
Next week I am going to do, I'm going to start off with the identification, and I'm not going to complete identification but go on to panel data, all right?